positioning. It's fine. Positioning within this workshop program, this might be fitted more the first week, because I will be talking on proton-rich site nuclei organic nuclei, on isospin symmetry breaking effects and the applications to thank you, to nuclear bit decay. Atomic Sai Wong is my collaborator. He actually started this within his PhD thesis around 10 years ago, and now he mainly continues to work along this line. Relatively less participated. So what I will be talking about a phenomenological point of view, or what I call theory on the experimental constraints, which is not that much popular these days with huge developments of ab initio process. But I will give some reasons that it still might be relevant for the topic on the study. And I will also show a few results from the non-partial model at the end. So the talk is combined from two parts. First, there is some background about isospin symmetry breaking, experimental signatures, and how well the shell model describes this phenomenon. And in the second part, I will concentrate more on the applications, and the main will be calculation of isospin symmetry breaking corrections to super allowed beta decay. We studied the framework in general. It is not a new one. We followed, of course, previous research in this area, but we made a few. A few revisiting or investigations of the application of the large-scale shell model calculations with Wood-Saxon or Hartree-Fock wave functions. We explored the effect of high order terms in this isospin symmetry breaking corrections, typically neglected within the shell model approach. And I will show first steps, or some steps in ab initio description. So sorry if I start two basic things. Isospin symmetry, as you know, was introduced by Heisenberg, who proposed to treat a proton and a neutron as the two charged states of a nucleon, and isospin formalism was developed in analogy with the ordinary spin formalism. So these three components of the isospin operate satisfies U2 commutations relations. Of course, it's a convenient way, for example, to express various operators. Here there are examples of electric charge operators in using this TZ component, or the ladder T plus T minus, which transform a proton to a neutron to a proton, can be used in the formulation of the decay, for example. Now, from the conservation of charge and charge independence of nuclear forces, Wigner introduced the total isospin operator coming from the couplings of individual isospins. If we consider a charge-independent nuclear Hamiltonian in the absence of electromagnetic interactions, it would fully compute with the components of the isospin operator. Thus, the eigenstates formed these degenerate multiplets and can be labeled as T and TZ quantum numbers. However, the isospin symmetry is approximate. As we well know, proton already are charged within a nucleus, and it was again Wigner, about 20 years later, who showed that the Coulomb interaction, written here, yes, with two-body interaction in isospin formalism, can be expressed as a linear combination of an isoscalar, isovector, and isotensor operator. So if one estimates the splittings of the isobaric multiplex due to Coulomb as an expectation value of this operator in lowest order, one can apply the Wigner-Eckert theorem in isospace and get this quadratic expression in TZ. Because relating to masses, one gets this famous isobaric multiplet mass equation. So A, B, and C are parameters which characterize the parabolic splittings of the multiplets one by one. What is interesting, this relation holds also for quartets, quintets, and higher order multiplets. All the deviations are searched for and actually difficult to be robustly described. To say also that this framework, so the splittings within the perturbation theory corresponds actually to this group reduction chains of SU2 to SO2, which is a subgroup. And this means this is called dynamical symmetry breaking. So the degeneracy inherent to the SU2 group is removed, but the quantum numbers actually is still a good quantum. So this another consequences of isospin symmetry, which still holds within this dynamical breaking, are selection loss for transition operators. So allowed Fermi and gamma-of-Taylor decay, here written in impulse approximation with one-body operators. There are isovector operators, so they have these traditional, as you well know, selection rules. The Fermi operator being SU2 generator has this analytical expression for the matrix elements without any with model independence. Electric dipole operator is also special, so its intrinsic part, this second term, the expression is a purely isovector, which means that in n=z nuclei, as shown here, E1 transitions between states of the same isospin would be proportional to this isovector Clebsch-Gordon coefficients, which is 0. Therefore, they will be absent, hindered, or at least suppressed. Another isospin selection rules for electromagnetic operators, assuming their one-body structure, which is a bit less known. Such an operator can be shown to be composed on an isoscale and isovector part, which means that if we would like, for example, to estimate the matrix elements of such operators between states of the same isospin within the isobaric multiplet, it is shown here, then these matrix elements will follow a linear train as a function of Tz. And on the left, there is a figure I took from these publications, which shows the compilations of some PF and SD shell nuclei, where indeed straight lines are found. So these strengths of the transitions between isobaric analog states, except potassium 38, which is still, I think, an open question for today. What is related? What is the problem? Now, explicit breaking of isospin symmetry can be observed to experimental signatures. These are observation of these isospin forbidden transitions, like Fermi transitions to non-analog states, or isospin forbidden E1 transitions between the same T states with the same T and n=z nuclei, or isospin forbidden particle emission. So this means that isospin is not a good quantum number anymore. One can think of some smaller mixtures of different isospins. So we talk about isospin mixing, and the rates of these events will be, of course, proportional to the amount of isospin mixing. So the question is how many body approach, modern approach, can describe all these such phenomena. Well, although small, they can be important for the structure of proton-rich nuclei along n=z line. They are vital, for example, for estimation of matrix elements of weak interaction for precision tests, and they're also very useful in, they are important in description of the astrophysical RRP process on a proton-rich site, which is a small a figure shown here. So this I will not talk very much about that. Now, the approach what we adopt is the shell model. I will start with the no-core shell model formulation because I will show at the very end some result. It was it's also called the configuration interaction approach. The basic idea is that the translational invariant Hamiltonian containing relative kinetic energies, nuclear kinetic energies minus the center of mass motion plus nuclear-nuclear interaction is diagonalized in a many-body harmonic oscillator basis. So the results depend on the excitation quantum of the h-barometer parameter of the basis and the size of the model space and number of quanta besides the number of excitation quanta allowed in your basis beyond the lowest polyprincipal out configuration. So the results are converged when the dependence on these parameters disappears. So the model space should be relatively big. The main advantage for this type of physics is that the Hamiltonian, the approach conserves all the symmetries. So we have solutions which characterized by good quantum numbers, by symmetries such as not angular momentum, isospin, if you apply, if your Hamiltonian is does not contain any charge symmetry breaking effects, and this is important for the description of what is related to isospin symmetry breaking. Now, for heavy nuclei, the dimensions become very large, and the approximations which I will use, so we use in our work, is the valence space shell model. So we solve this eigen problem only for nucleus situated in a model space beyond the closure core, which means that we have to work with a kind of effective Hamiltonian such that in the model space, using model space decomposition of the wave functions, we could get at least some subset of low energy eigenstates. Such a Hamiltonian written in the Fock space here, with the subtraction of the core energy, is fully determined by the set of single particle energy two-body matrix elements of the residual interactions. For convenience, one can introduce this auxiliary harmonic oscillator definition. There are two ways to get those parameters of the model, those two ingredients, either derive them microscopically from the nuclear-nuclear interaction or to get them from experimental constraints or phenomenologically. And this is something which, the second approach, which provides a shell model with a lot of successful descriptions of nuclear data at low averages, as we know. Now, how these schemes incorporate isospin symmetry breaking. So in ab initio approaches, one starts with the very nuclear force, and this is known to be charge potentials known to be charge dependent. So if we talk about these sources of isospin symmetry breaking, d quark masses and electromagnetic interactions between quark. On a nuclear level, we talk, our language is this long-range Coulomb interaction between protons and APs appearing in the due to the difference of proton and neutron masses and charge-dependent forces of nuclear origin. So the evidence of these charge-dependent components comes already from the nuclear-nuclear scattering. So we know in the 1s0 channel, for example, the scattering length of neutron minus proton is slightly different, which evidence of the presence of the charge symmetry breaking of the nuclear-nuclear interaction, proton-proton and neutron potentials are slightly different. Even a bigger difference comes from the difference of evidence from the difference of scattering lengths, the average of the proton-proton and neutron-neutron minus neutron-proton. This signifies the presence of the charge independence breaking component of the nuclear-nuclear interaction. Proton-neutron and T=1 channel is more attractive than the average of the proton-proton and neutron-neutron. So these are in our previous language something which can be called as a vector and isotensing component of the interaction. There are other nuclear effects such as the Nolan-Schiffer anomaly or simply the binding energy difference of the two lightest mirrors, hydrogen and helium-3, which requires the presence of discharge-dependent forces of nuclear origin. As I said, modern high-precision potentials, CD-Bon, argon-15, chiral F-T potentials, they include discharge dependence in their formulation and then can be applied in ab initio approaches. So there is a very nice description of isospin symmetry breaking a light nuclei up to boron 8, published in 2013 from Green Functions Monte Carlo. So how to incorporate all this in valence space calculations, and I think the most cheapest and way, which was developed by Alex Brown and Eli Horvan still in '89, is to add to a good valence space isospin conserving Hamiltonian piece which breaks isospin invariance, which is composed from Coulomb and this charge symmetry breaking and charge independence breaking effective forces which can be modeled, for example, by a Rho exchange potential. Then one also needs to account for the difference in single particle energies between protons and neutrons. There are a few parameters, but not that many, so which can be constrained in the following way in a perturbation theory. So one evaluates the splittings of the isobaric multiplets between the states of good isospin already obtained with isospin variant Hamiltonian, and one fits these P and C coefficients theoretical to experimental coefficients, and those are databases. So, and I think this allows to get very precise sets and very precise Hamiltonians to demonstrate the B coefficients for doublets and C coefficients for triplets are shown here for SD and PF shells. And we see that agreement with the experiment and theory is very good. The RMS errors are summarized in this table, and this is the number of data which was used in the fit shown here to the right. So for SD shell, ground and excited states, one for PF shell only lowest multiplets were taken into account. So this is something to be compared. There are also attempts microscopically derived interactions from charge-dependent potentials to reproduce these effects within many body perturbations. I don't show any figures. The description is not satisfactorily, and here's the only another ab initio approach which I took from comparison is from IMSRG group, published in 2021. So B and C coefficients are calculated for triplets. So these are not all even A, but those which are which allow to have an N-eclosive ordered nucleus in the middle. So this upper line C coefficients and some the corresponding B coefficients these are, of course, very fundamental calculations with the chiral potentials. The pink and blue bands show so the theoretical intervals of such coefficients, error bars included, but we see that there are already for C coefficients quite off the experimental trend. And to show that this is something which stays to be challenging. Now, to demonstrate a few more capacities of the phenomenological shell model, I will show B coefficients for doublets and triplets. We see that there are some wiggles are present also actually for C coefficients. This is due to the properties of the Coulomb interaction and its contribution to pairing. Here we looked through differences in B coefficients for neighboring multiplets, which shows this very peculiar staggering again for doublets and quartets, and we see that the shell model managed to describe those fine structures very well. Here is another demonstration by considering these multiplets not only lowest in energy, but the first and second excited multiplets, B coefficients, differences in B coefficients for doublets in the top row, and C coefficients for triplets in the lowest row. So red, blue, and green are different excited multiplets. Experiment will proceed, and we see that qualitatively, quantitatively we did not assess, but qualitatively there is a relatively good agreement. This allows quite important applications to mass predictions. Again, here this static, I think it shows here right from the work by Alex Brown and Bernard Lichter from 2011. And this is based on the interesting fact that if you take an isobaric mass multiplet equation, for example, for triplets as shown here, you see that A, B, and C coefficients can be expressed using the three masses. So for nuclei along n equals z line, if you know like the masses of n equals z, the neutron-rich mirror, you can, or excitation energies, you can apply theoretical C coefficients to predict the position of the excitation energy in your proton-rich partner. And this is something which works relatively well, knowing that the precision of C coefficients is quite high, around 10 keV. So this opens importance for nuclear astrophysics. Now, how all this theory describes isospin forbidden transitions. Here I'm more skeptical. This is still challenging, and this is due to this way. Because if we take a Hamiltonian and now we diagonalize it, we get states of the mixed isospin. Isospin is not conserved anymore, therefore it can reproduce isospin transition rates. Why the description is difficult, the example is shown here. Suppose that we have two states of the same spin and parity by different isospins, and the Coulomb interaction, isospin symmetry breaking interaction, it mixes these two states. So the mixing amplitude, so just the simplest two-state mixing, will be squared, will be proportional to this charge-dependent matrix elements squared divided by the energy differences. So while this mixing matrix elements of charge-dependent interactions from all our work on this proton-rich site, it looks at between low energies, this shell model gives quite reasonable agreement with experiment. These are highest values known experimentally for PSD and PF shells. So this is something which is 10 keV. This is at most reaches around 100 or 150 keV. However, the energy difference is challenging, and you imagine if you have around 200 keV uncertainty on the position of the level, this delta E squared, this uncertainty would give a very huge uncertainty on the amount of isospin mixing, and all your transition amplitude will be, transition matrix elements will be proportional to this square. So this is why if only we have a possibility to scale or to relate some other experimental constraints, one can rely on theoretical these mixing elements. So this complicates direct prediction of isospin mixing, and similar what I maybe mentioned, the search for the cubic quartic terms in the isobaric mass multiplet equation. This is all beyond the precision of I present. So now the second part of my talk, how this framework can be applied to nuclear beta decay studies, and this is the first or the most important application is the computation of isospin symmetry breaking corrections to supernow 0 plus beta decay, because the matrix element is model independent, and this correction actually represents your realistic your realistic matrix element to contribute to this extraction of the weak interaction data. So the standard model of particle physics known to be the best physics model which exists, but this is also an object of experimental verifications. Two types of tests are performed at high energies at large colliders, or at low energies in precision measurements, such as in nuclear beta decay, and the nuclear matrix elements are needed to relate so the measurement to be able to extract the information relevant to the weak interaction. And I will focus on the Decay matrix, which is appears because some mass eigenstates, weak quark eigenstates are linear superposition of the bias eigenstates. So the matrix elements of this Decay matrix describes the relative probability of a certain downtime what to be transformed in another terms. So the standard model does not predict numerical values of this matrix. They have to be found experimentally. The standard model does predict that or does prescribe that this matrix has to be unitary. So the determination of VUD shown here is the matrix elements contributes to the normalization condition test of the upper row. When aware how it appears, so VUD can be extracted from the isolation of the weak interaction couplings govern this semi-leptonic decay, over purely leptonic decay, this universal Fermi coupling constant. And there are a few four physics possibilities, and where such for physics cases where these measurements are possible with different difficulties, like type of beta decays, super 0 plus, or mirror decays. They have one of difficulties to handle nuclear structure effects related to this isospin symmetry breaking, apart from radiative corrections and Fermi to gamma Taylor ratio is mentioned here. Neutron decay, this is a lifetime, but so there was much improvement in this area in the last couple of years. And finally, the pion decay, which is a non-baryonic decay, but the branching ratio is very small, and this poses another difficulty. So we focus on the first option, and this is a decay of a nucleon inside the nucleus, as shown here. In general, the decay rate for types of excited transitions, Fermi gamma Taylor, can be expressed and shown by this formula. So in GV, this is a weak interaction coupling for this electronic decay. K contains various universal constants. GV and GA are weak and axial vector and axial vector coupling constant. F is a statistical wave function, slightly different for vector and axial vector transitions, and MF and MGT are the matrix elements. It was noticed already in 50s, soon after Fermi, after formulation of the relation of the conserved vector current hypothesis, that 0 plus decay does not contain Ricard component, and therefore the constancy of these values throughout various emitters fixed isospin will be one of the confirmations or verifications of the conserved vector current hypothesis. And if valid, one can extract this GV coupling constant. The data shown here almost for all 14 cases which are known currently with precision better than 0.4%. There are a few points which are missing in this plot, but in any case, from this experimental data, this experimental half-lives, from the measured half-life and branching ratio and the times statistical wave function, statistical rate function, where the Q value, another experimental quantity which enters in. So these data are not constant at all, as seen in this plot. Another maybe remarkably done, so the plot comprises data with some data with very small error bars and some data with large error bars. Data with small error bars, these are transitions from TZ equals 0 and equals 0 emitters. They are not with much better precision. Those which have data points large error bars, these are transitions from TZ equal -1 hotness. So the large error bars is due to the complications in the determination relatively precise of the branching ratio, and except of these two highest emitters like 74, where the branching ratio problem is still an open question. Now, as I said, we see that the data are not at all constant. They grow up as Z grows up, and this is normal because what is not considered here is the electromagnetic corrections or effects due to electromagnetic interactions, and they increase as they increase. And the best way is, or what exactly should be constant, this is what we call the absolute FT value, the one which is calculated from the experimentally deduced small FT values by imposing various corrections. They are written traditionally in this form. In red are primitive corrections, which can be nucleus independent, nucleus dependent, dependent corrections, and in blue is the nuclear structure correction due to deviation of the realistic Fermi matrix element from its model independent value squared. So there was a lot of activity in recent years within newly developed effective field theory approaches to reevaluate radiative corrections which impacted the field. Also, renewed activities to get nuclear isospin symmetry breaking corrections. For this, you need a many-body approach which exploits charge-dependent forces and which describes this isospin symmetry breaking on the question. So there have been, I was talking about the shell model, but there have been many developments in other approaches, including those which were applied for systematic calculations of these isospin symmetry breaking collections. So there was approach by relativistic RPA and angular momentum and isospin projected density functional theory with a functional including isospin symmetry breaking terms. So if we plot various predictions, model predictions, like collections as for those approaches who provided a universal set, we see that there is a huge divergence. To get out of this, Downer and Hardy, these are who master this domain from 70s, they proposed a test that they accept, assuming all other corrections, quadratic corrections fixed, which exactly model gives you agreement with the CVC hypothesis, and then only shell model with Saxon, which could pass through. And applying that, we get indeed that from non-constant set of FT values, quite a flat region of the absolute FT value, quite a constant band comes out, and this is in agreement with the CVC with chi-square p nu 0.5, which allows to extract VUD. So these numbers are taken from 2020 when a new value for this capital delta correction was proposed, and this one, this was the main reason that the normalization condition for the top row of the Decay matrix was not exactly matched, and there is some tensions. So since then, there is a lot of work. Some review can be found by Seng and Goldstein, published in 2023. We arrived to this domain a bit around 10 years ago, and the reason was to have again look from on the shell model calculations similar to what was done by Towner Hardy, but stress on the isospin on large-scale diagonalization, on more universal parametrization of these isospin symmetry breaking terms, and to revise to perform an alternative set. So the shell model description of the Fermi matrix elements is shown here. So in the second quantization, the matrix elements, as we know, is expressed by the one-body transition densities times the radial overlaps. So there are two sources of deviations of or inclusion of isospin symmetry breaking effects. First, taking the wave function, initial wave final wave function coming from the isospin non-conserving Hamiltonian, the one-body transition densities are deviated from those calculated with isospin conserving Hamiltonian one, and the second deviation comes from the radial overlap with this single particle matrix element. So if proton-neutron wave function are taken from a realistic calculation, not from the harmonic oscillator, but from both Saxon or Hartley-Fock, including Coulomb interaction, so this overlap will be different from one. This formulation misses something. I put here reference to Miller and Schwenk. We are currently working on this verification. So this operator is not actually an exact isospin operator, because it misses in this formulation couplings. We call it radial excitation of of the overlaps between protons and neutrons with the same quantum numbers, except the main oscillator quantum numbers, so from high-lying shells. How it's not very easy to assess it, maybe I will say a few words at the end. Now, the correction can be expanded in terms of small quantities due to isospin symmetry breaking effects. So this deviation of the one-body transition densities from the isospin conserving values and deviation of radial overlaps from one. Strictly speaking, the exact direction, if we consider this relation, because the matrix elements should be squared, it contains 6 terms, but they have different order. But the leading order terms, these delta C1 and delta C2, are typically considered, which are linear in these small quantities shown above. But there are also next to next leading order terms, and I will, for the moment, we skip, but we have evaluated them to see how robustness the linear approximation is. So we performed the shell model calculations using these model spaces with best available up-to-date interactions. And this is up to actually bromium 70. Rubidium 74 is not reachable for the moment by these techniques. The shell model calculations of delta C1, so due to isospin symmetry mixing, this is actually characterize the depletion of the Fermi strengths between the isobaric analog strengths. To get it, the way we computed, we summed all non-analog transitions within the available model space up to 100 or something, it was up to 500. So here is the example of mass 62. 2 different interactions give this running sum, which starts to converge at some point. We scaled with energy, as it was explained, that this splitted components of the Fermi strength, it is proportional to the isospin mixing in the considered space, so the mixing between non-analog states squared. So this scaling provides an important ingredient in the values, and some results are shown here in comparison with the work of Tanner and Hardy in red, and with calculation by Alex Brown and Eric Ormond by 95. Now, to get the delta C2, the correction due to the deviation of the radial overlaps from one, one can not simply rely on the one-body transition densities, but one has to insert here kind of resolution identity to make a sum of all states of the intermediate nucleus. It is shown in this cartoon. So instead of using transition densities between the initial and final state, we compute all, we insert the sum over intermediate states, which can be coupled by the operator. Then the expression involves the spectroscopic amplitudes for the proton and neutron emission and the radial overlaps, which will depend on this intermediate state spike. This is an important ingredient, because it the radial wave functions, they will depend on the depth of the potential. The depth of the potential should be such that it reproduces the proton and neutron separation energies. So in this work, if there is any experimental information on the spectroscopic factors which enter in this computation, at least for low energies, it can be a good help and verification. Now, the Wood-Saxon potential, usually it is something considered very, very simplistic. But we also know that the various parameterization can give very, very different things. And the way to constrain was to make a fit and adjustment simultaneous of the potential depth shown here, V0, and the radius parameter R0, which enters in the definition of the nuclear radius, so that to match the experimental nuclear separation energies, including intermediate states and to compute correctly the measured charge radius for one of the daughter parent nucleus when known. And here we introduced also the complete sum of intermediate states, so we go beyond the closure approximation. These constraints, thank you. So these constraints are important because the correction evolves as shown here. Very much depends on the difference in single particle energies, on the charge radii, and eventually spread can be done if we allow the diffuseness of a potential to be allowed. So this is something, the results, which are basically consistent with the work of Turner and Hardy with smaller error bars. But then our last thing, what we explore is to allow additional uncertainty on the diffuseness parameter, and this brings to some final results on the FT value, which is shown here in comparison to those of Turner and Hardy by 2020. So we get with an increased error bar, an FT value which is a little bit high, unfortunately, because it will produce more tension on the CKM similarity, but which is really reasonable, which is with a relatively reasonable chi-squared deviation. Now, briefly, I will say that we followed the work of Alex Brown and revised the application of the Hartree-Fock wave functions in this analysis using, again, a scaling method of the potential. And the results are shown here. So besides this Hartree-Fock main calculations, we also did a careful analysis of the suppression of isospin symmetry of spurious isospin mixing in the states, introduction of the charge symmetry breaking charge independent terms in the density functional, and a few other corrections. So on average, we got that the result compared to the pure Skern calculation, the correction becomes larger. This was always a problem. However, in our opinion, there are still what we call post-Hartree-Fock effects, which are missing in these evaluations. And this is due to the Hartree-Fock calculations for a node nucleus. So this is something which cannot be accounted. Most probably we would rely more on the Wood-Saxon analysis. This Wood-Saxon wave function in this domain. So finally, I also would like to say about higher order terms in the computation of the correction. So this plot shows how delta C evaluated from the matrix elements compared to the linear approximation when we separate, when we keep only linear terms in the correction. In blue, this is a linear approximation, which is already with 100 intermediate states becomes converged, while the computation of the realistic Fermi matrix elements requires a lot of intermediate states to be converged. From this analysis, more or less, we see that we have not seen any deviations for the results. However, to get for more emitters the final value of the correction faster, we compute those delta C3, 4, 5, and 6, what we call next leading order terms. And we see that so the delta C3, this is a second order correction, which proportional to the product of the linear terms described above. And the last four can be expressed in terms of the first three. This is beyond, this is within the closure approximation, but beyond the closure approximation, it's a bit more complicated, but the relations stay close. Estimating of all this will give us the exact result, and the corrections are shown here in this plot. So except for these two heaviest emitters, for which non-negligible contributions of delta C3 are seen, for all the rest, the approximation is basically valid. So no criticism should be one cannot bring any more criticism to the separation. And in my very last slide, I will show first some attempts to understand the initial no-partial model application to calculation of the Fermi beta decay. So first computation with the no-partial model was done in this work by Proton-rich, Etienne Collier and collaborators in 2002. They used this charge-dependent CD bond potential to compute the correction of the carbon-10 beta decay. As seen on this figure, it is not, it seems not to be really converged. Also, some estimation from extrapolation techniques as a reasoning has been presented in that work. Later on, I did not find publications, but I have a talk by Michael Kruse, who explored the mass 6, helium 6 to lithium 6 super allowed decay, which is not among the studied emitters known with good precision. But what is interestingly here, so much larger model spaces became available. This is a two-body probably and three-law interaction. We see that the convergence, the correction continues to increase without any hint on convergence. So that was quite worrying. I don't know exactly the status of whether no-partial model experts continue to investigations in this domain. What we undertook, we took the simplest case, tritium beta decay, and looked at convergence of Fermi and gamma of Taylor matrix elements, and these results are presented here. So from about nmax 20, so there are possible up to some, we see that the correction, Fermi correction converges. So for gamma of Taylor, this was is actually SRG evolved interactions which use the two-nucleon interaction. And here in dots, there is also a consistently evolved gamma of Taylor operator, which was used. So if I concentrate on the Fermi transition, this correction comes out to be converged to this value, C small a 0.053% from about nmax 20 if we consider these lower H bar omega values. So this is something to understand how what procedure can be proposed to accelerate convergence, because we would really like to have these values for light nuclei like mass 10 or 14. So we work on this with some non-orthogonal basis, but this is about for the moment no receipt or no procedure came out from this work. So in my conclusions, I showed this isospin symmetry, highlighted some facts on isospin symmetry breaking, and show how modern phenomenological shell model how well can describe those things. And the main application was done to the calculation of this isospin symmetry breaking corrections to super allowed beta decay. So we continue to work on this. So Latsanik Saivon is the main person who pilots this project, maybe to improve our current calculations and maybe approach heavy nuclei along an equal zip line. Thank you for your attention.
Thank you. Okay, I have time for a few questions. Are there any questions in the audience?
Yes.
You know that in EE prime P that the spectroscopic factor is only about 60% of the shell model wave function.
Yes.
So it seems to me that one can't make much progress until you understand how to incorporate that.
So you mean
in these type of calculations. You got a slide back there where you expanded over spectroscopic
Yes.
factors, and that's not 60%. It's more like 90%. Anyway, I think that's a problem. And I always ask the ab initio people, what do you get for spectroscopic factors?
So the quenching of spectroscopic factors towards neutron-rich side, or
No, N equals E,
N
stable
equals E.
nuclei with the E prime P. And it goes from calcium 40 to lead 208.
okay.
You know, they see 0.6.
Yeah, this is a very good point.
So it's a question. And maybe you could tell us, you showed at the very beginning that unitarity was violated at some level, I mean, small. What would you have to do to delta C in order to make agreement with unitarity?
Okay.
It's a simple question.
Yeah, this we had a look, a kind of pragmatic question. I cannot say immediately. So our FT value comes out to be too large, which means that delta C should be then smaller.
I see. So you want the delta C to be larger or smaller?
Or maybe
You want delta C to be larger or smaller?
just a moment. Yeah, let's have a look together. So delta C, I know it should be larger than to have FT value smaller. This was minus.
In other words, to make VUD larger.
Yeah, so yeah, Thomas, this is larger.
You need to make the delta C smaller.
I think we need to make it smaller, yes, because the large FT values actually we get it larger, unfortunately, and this goes not in the right direction.
Right.
Yes, this might be this question of spectroscopic factors.
Well, that and there's other issues, but I mean, that's an obvious one.
Because the quenching would definitely quench the delta C2 correction.
Good. Any other questions? Actually, while we're on this slide, so this is not one, right? It's not consistent with one.
Yeah.
Is this okay because of union? I don't know, 2 sigma?
Yeah, it's what was in 2020 called the kind of tension on the first row. But since then, there are so many results on re-evaluation with different approaches, dispersive relation from AFT lattice calculation of various corrections. There was a measurements maybe of VUS matrix elements because it's also not evident which value exactly to use. So there is some similar in the review by Seng and Goldstein. The relation is different, but not very different from what it's now. There is a kind of the tension of the same level, which says, but it's an open.
At the beginning, Towner and Hardy got 1
Yes.
in the sum, and they were happy for some years until the US changed or something like that.
Yes.
There's an issue in science that you work and work until you're happy. But now you're not happy and you have to do more work. In other words, I think they quit too early.
Well, I mean, the last one was this 2020 review, no?
No, but this was 10 years before that.
Okay.
Yeah.
They've been doing that forever.
Yeah.
Right.
Or even more, then there was this inclusion of spectroscopic factors contribution from.
Right, you keep thinking of things that you need to change in order to get something, and when you get one, then you sort of quit thinking about what you need to change because you're happy. Anyway, it's a philosophical issue.
Okay. I'm gonna ask this one quick question from Zoom, and that's it for over the hour. So Praveen Srivastava is asking, is radiative correction sufficient if we consider only leading order? I think no need to take higher orders such as NLO, etc.
Which in
It shows the radiative in radiative corrections.
In
he's
radiative
asking
correction?
if
I
leading
did
order.
not work on that. So in evaluations of FT values published values, you know. What I was shown, these are next to leading orders. Beyond this separation, and that's for the corrections that only 2 leading order terms are taken. So for us, the others are small unless for heavy nuclei or if one goes to the decay of T equal to to integral to other bioeconomic states, and they become large. But this is a precision is not sufficient yet to be included among the best transitions. But this is something we need to.
Sounds good. Okay, we're on top of the hour, so let's thank the speaker again.
More